Recording is on.
Okay, hi everybody. So, we are going to discuss some of the concepts in the trees. So, we already covered so many problems in the trees, right? So, we covered, BFS, DFS, binary trees, and balanced binary trees, and minimal trees, heaps, max heap, min heap. So, we covered many of the problems on the heap. So, today's problem is first common ancestor, like finding a first common ancestor. This is a very popular question, and this is in the sixth edition of on the page number 110 in the cracking the coding interview book, sixth edition. So this is the algorithm we are going to discuss today. So the main problem here is find the first common ancestor of two nodes in a binary tree. This is the algorithm, this is the kind of question. So we'll go through that today. So let's go back to the board. Let me write the tree. So here is our tree. Okay. So binary tree. Basically, binary tree, we all know that root and left and right. So only two children for any node, right? So this is not a, and make sure this is not a binary search tree. So binary search tree has its own definition, right? With all the integer values and, but this is just a normal binary tree. Okay. Now we need to find first common ancestor. So what is first common ancestor? Okay, let me use this whiteboard to draw. So yeah, Karan, any idea what is common ancestor?
Are they referring to the common parent?
Exactly, common parent. Exactly. So let's have this. Let's say we have these elements like this, right? A and B, C. B has children D, E, right? And E has H, and D and H. F. D has F, G, and this one is I. Okay, now if we go back, so now we need to look at what is the parent of F and G. So for parent of F and G, like this is the same parent, basically F here and G here, the parent is D, right?
Yeah.
But if you look at F and H, let's say if you consider F and H, so they are very far from in the tree. Okay. Now we need to find common ancestor. Maybe ancestor means just the one who just where those two will meet. If you go back to the parent, if you go back to the root, hey, this is so D is his father and B is his father. Okay, let's say, and this B is father for E as well, and E is father for H. So if you go back, right, where they are meeting, they are meeting at the B. B is the actual grandfather for F and grandfather for H. So that is the first common ancestor, right?
Okay.
Now again, B A is the father of B, let's say, and A is also second ancestor. If you go back to the A, B is my grandfather, and H will also say, hey, B is my grandfather. That's where these two people meet. Basically, their ancestors meet. Basically, same ancestor. You got it? So
Yeah.
basically, yeah. So this is the B is the first common ancestor. So you see, this is also ancestor. Ancestor means basically the previous generation people, right? It could be father, it could be mother, it could be grandparent, or anybody. So he is also ancestor, even though he's a parent, he's also ancestor, but it is not common, right? Because F has D is the ancestor and E is ancestor. So this is not common ancestor. But if you go up one level, B is the common ancestor for both F and H,
Okay.
and A is the second common ancestor. And if you go up again, if A has another parent, that will be the third ancestor, right?
Okay.
But we don't need to go that far. Basically, our answer is B. If I give you F and H, the answer should be B.
Okay.
Okay. What is the common ancestor for I and H?
Shoo, shoo, shoo. Yeah, Suresh.
No problem. Yeah, you want to speak?
No,
Yeah,
no,
no
no.
problem.
No, no, no.
So I'm asking you, what is the common ancestor for I and H?
Common ancestor for I and H is B.
Again,
Same.
B, because if you go up again, they will meet at the same location. Yeah. What is the common ancestor for F and I? F and I.
F and I is D.
D.
Yeah.
Because they are meeting here itself. If you go back, they will meet there. Simple.
Okay.
Yeah. What is the common
So,
ancestor? Go ahead. You do you have a question?
yeah, so for this, do we have to maintain an index of ancestors of
Yeah,
each
we'll
one?
we'll come to that. Exactly. That we'll come to that solution. First of all,
Okay.
we want to make sure we are good at the understanding the problem. What is the
Okay.
common ancestor for E and H?
E and H, it is B.
What?
E and H, E is a ancestor of H. The
Exactly. So what is the common ancestor?
E.
E itself. Basically, common ancestor
Okay.
means basically where they meet. Basically, it's a so you can think of E as an independent node and H as independent node. Where they are meeting, they are just meeting at E itself, right?
Okay.
So you know, if you are looking in normal relationship, it doesn't matter. What is the common ancestor for a parent and child, right? He is not himself a common ancestor, but in this world we can think of like that because they where they meet each other. Okay,
Mhm.
so you can think of like, hey, we don't. If you did not look at the tree, if you just blindly say he and H, hey, he is a person, he is a person Suresh, and H is a person XYZ, and we'll ask, hey, where you guys will meet, like what is your hierarchy? I will say, hey, this XYZ is the child of E. Okay, these are just child and parent, so you can think of E as the ancestor for H, and that's the mating. So that's just a little bit deviation from the normal parent child relationship kind of ancestor relationship. But if you think as a path, basically you start here and you start all the way to the root, and you start somewhere here, this will also go to the root. This is where they are meeting. That is the common ancestor, right?
Okay.
So basically the idea here is your I gave two nodes. One node is here, one node is here in the tree.
Okay.
Basically, this every node in the tree, if you go up, every node in the tree goes all the way to the root, correct?
Yeah.
And even this node is also root, go to the root. At some point they will meet. That is the common ancestor.
Okay.
So if in the case of E and H is going like this, like this, and like this. Now E is going like this. He is here, like this and like this. So both will meet here itself, right? So
Hmm.
this path is going this way, and even he started from here. This path is also going this way. So this is where both the paths will collide. So that's why
Hmm.
the common ancestor. You
Okay.
understand? You
Yeah,
understood the
yeah, I
problem.
understood. I understood.
So now how are we going to solve this? It looks like bottom up PP5, right? Just like because you are going from bottom to the top, right?
Uh,
Which is kind of navigation, but of course, but this is not representing an array or anything. That's why don't think that we need the formulas or anything because it's just a normal tree data structure. I will give you the tree as it is, like our previous problems. We have root, left, right. Yeah. And you
yeah.
asked a very good question in the beginning, like yeah. So, how to navigate from bottom to the top? You always navigate like if you are here, you know this is, let's say this is n dot left is this one, n dot right is this one. You can if you are here, you can easily go to down and right and left. You can go down, but how do you go up? right? That's why you
Yeah.
asked about, do we have a access, can we access a parent, right?
Huh. So I have solution, but it will cost space actually.
Yeah, basically there are two cases here. Either, yeah, go ahead. Yeah, what is the solution? Yeah, I
I
would like
This
to.
is my solution. I don't know how far it will work.
Yeah.
So for each node in the tree, we are maintaining its ancestor node, current ancestor node. For example, for A there is nothing. For I
Mm-hmm.
it is G. For G it is D, and for F it is D. Uh,
Yes.
for example, if we want to find for F and H in the first case of,
Mm-hmm.
okay, so we already maintain an index for H. It is H. For H it is E, and for E it is B,
Yeah.
and for D it is B. So
Yeah.
for F we look at it index which is D, and for D we look at the index which is B.
Mm-hmm.
And the same way for the H, we look at the index which is E, and for E, we look at the index which is B, where uh, two two children nodes meet at the B point. So I'll end it up the common ancestor.
Exactly. So basically, you will look at the each time you jump there, and hey, see, is both are same. So basically,
Yeah,
you will start from F and H. Both are same.
yeah,
No, you can simply take P or Q. These are the two variables you take. P points to F and Q points to H, and you will see both are same. No, then P becomes D, right? P points to D and Q points to U. Basically E.
yeah,
Basically, using these pointers, you can go to the parent and you
yeah,
compare, is D and E are same? No, these are two different nodes. Then P points to B and Q points to B. Now both
yeah,
are same.
yeah,
Then you found a common ancestor, right?
yeah,
That's good. This is exactly the algorithm number one. So that's very good. Um, uh, so basically you are maintaining not only left and right, you are maintaining parent as well,
yeah,
right? So
yeah,
there are three pointers. The node, if you look at the node class node class format, there will be a first one is data. We need to know the data. What is the data? Is it A, B? Basically the value here. It could be integer, it could be employee, object, whatever the data. And the next one is left, the left node, and right node, and then next one is parent.
yeah.
So there are four properties. One is left and right, and which is very common, and data is also very common. We have that either integer or character, anything. And the next one is the last one is the parent. So that will tell you for any node, if you say what is the parent, it will give you the parent node.
Hmm.
Using this, you can definitely navigate up from bottom to up. You can easily navigate, right?
Hmm.
So here is a problem here. So you are looking F and H. Let's do the same problem for um, I and H. What is the value? What is the common ancestor for I and H? Again, B,
B.
right? Can
Yeah.
we do the same approach if you use P and Q? Can we find B? Let's see what happens. So what I'm doing is I'm going to create the table. So first you initialize. This is the table. So this is P and this is Q. First you initialize with, because the algorithm already giving two inputs. Hey, here is the, you start here and you start here, find this one. This is what we need to find, right? So you already know you already have a pointer to this. This is P, I, and this is Q, right? So what is the common ancestor for B and B? Let's say if I'm giving both same values, it's exactly the B, right?
Hmm.
So first step is you compare whether these two are already equal.
Hmm.
So is P equal to Q?
Yes. I mean, here I and H it is not.
I and H. Let's talk about I and H. So
No,
that's the
it
first
is not.
step. Whether you gave two nodes, is two nodes are same. If two
No.
nodes are same, then that itself is the answer.
Ancestor. Okay. I and H is not equal.
Not equal, then what you do?
I'll
As
go
per
to
your
the
law,
parent.
exactly, you go to the parent. Now P becomes,
P becomes D.
no, we started from I.
Oh, sorry. P becomes G.
G, uh-huh.
Uh,
Q becomes,
Q becomes E.
Q becomes E. Now let's compare.
No.
Is P and Q. P equal to Q.
No.
No, right? Because you are comparing G and E. Okay, now what you do? P equal to,
Uh, D. P equal to D.
Q equal to,
Uh, B.
Q equal to B. Okay. Now what you do?
Now I'll
P
compare it.
equal to
It's not equal.
not equal. What happens now? P becomes,
So okay.
let's go with the algorithm. Let's see what happens.
Okay. P
Because
becomes B
P becomes B,
and
Q becomes
Q becomes A.
exactly. Yeah. Now are we is both are same?
No.
Okay. Now what you do? Let's go to the next level. What is the parent of B?
A, and there is no parent here actually, which is A.
Yeah, parent of A. What is the parent of A? If you go to
A.
the no, parent of A. Is there any parent of A?
No, there is no parent of A. That's
Then
why.
what is the value of a pointer if there is
0,
nothing?
null, null.
Yes, null. So now you are comparing A is P and Q are same now. You are comparing A and null.
Yeah.
What? A equal to null? You are comparing
Uh,
P and Q. So you're comparing the value of A equal to null. Is
null.
is both is this condition true?
No, this is
No.
not
So
true.
what you do? Go to the next step. What you do? So what is the parent of A?
Parent of A is A.
What?
No,
Parent
null.
of A?
No,
Null.
it's
Okay.
null.
Yeah. Now what is a null of null? Now parent of null.
Null.
Null. Basically, you don't even go because yeah, object is null. You cannot even access left or right or anything. Null.
Yeah.
So finally you reach null. Now this condition becomes true. Hey,
Yeah.
we found common ancestor. What is the common ancestor?
Null.
Null. Return null. Is that correct answer?
No.
Then where our algorithm failed? It worked for
Algorithm
F
phase
and
is
H.
maintaining the levels.
Yeah. What is that?
Maintaining the level. The level of
Maintaining the level. So
tree.
why it worked for F and H and why it did not work for I and
They are in
H?
the same level, but I and
Ex-
H are in different level.
Exactly. That is a very good point you found. The here, if you start at the same level, then it will work because you are navigating at the same speed. Just like two cars starting from one location to another location and they are going with the at the same target. There is a flag from 2 miles from here. Everybody will try to reach that flag. At some point they will meet.
Hmm.
You take different routes, but at some point, because it needs to go to the route, at some point, maybe at least at the flag value, at least at the A, they need to meet. They will meet.
Hmm.
But if they are not at the same level, one guy is starting 1 mile from flag and another guy is starting 3 miles from flag, but both are going at the same speed. Both are at the 100 miles per hour, let's say, or maybe if it is 3 miles and 3 miles and 5 miles, right? Let's say everybody going 10 feet per minute. So if both are going same speed, right? What will happen? Always the one who near to the flag will win, right?
Hmm. Yeah.
So then you never be able to meet same time. Somebody will win and then some other people will come along. So now you started at I. Before I reaches B, H already reached B, right? Here
Yeah.
is the thing. So use Q, basically P and Q already met B, but P is at the D location. at the time.
Okay. So, if is it possible if I maintain the level of each node,
Mm-hmm.
so that we can compare it, right?
Okay, but if you get the level, definitely we can maintain one more integer value here, and we can maintain the level. So what do you do with the level? So at the starting of the algorithm, you see the level of I is 1, 2, 3, 4, 5. The level of I is 5, and level of H is 4, right? 1,
Yeah.
2, 3, 4, right?
Yeah.
And what you do with this?
Uh,
This is exactly the interview question. Basically, in interviewer they will ask you the same thing. Okay, very good. Let's take one more variable. You have those two things. What do you do with those? How they are helpful?
if if
If both are not
both of the
same.
levels are not equal,
Mm-hmm.
or else we'll pick the.
Very good. Very you are thinking very good. So let's see what you do. So now I and H are I level is 5 and H level is 4.
Okay. So we'll compare from the fourth level of I.
Exactly. That is a very good point. Let's assume I is like you starting at this level. Let's say you want to know the ancestor of this node and H. So that means let's say this node is K. This node not I is starting at K. The Kth level is 11 and H level is 4, right? H is still 4, but K is somewhere around 11. 11 is 11 nodes deep from the root. That is the level, right? So now what you do with this, you should not compare this, right? If you compare this, H always wins because H is very near to the root.
Hmm.
So what you do, you will wait until the
Both of
K
them in the same level.
both are at the same level. Very good. Very good job. So you need to jump to the parent until you are at the same level. Let's say G and H are same level, right? You start from K and you jump all the way to here, and you are at the G and H. Now let's go with the same speed both the nodes. Correct?
Okay.
If it is I, just one jump is enough. So how many times you need to jump? How do you know that? Because so you got 5 and 4. That will give you the hint for you. How many times
Minus
you need
one. One jump is needed. 5 minus 4 is 1.
exactly. You need to do the delta. You need to sometimes this value is bigger than this value. We don't know. Like always, so let's say it's so the height of the P is bigger here, but there could be a case where height or the level of the Q could be bigger. So in that situation you will get minus value, but it doesn't make sense. You just need to take the absolute value. Okay, so
Okay.
you need to do the difference of these two levels, and you will find the difference that is called difference, or let's say diff. The difference is 1 here, but in this case what is the difference here?
11 minus 4 is which is 6. Sorry, 7, 7.
7, exactly. So 7. So there is a 7 level difference between these two nodes. So let's say K and H. If you are comparing this K and H, there are 7 levels or difference. So that's why you should not start H until these 7 levels are jumped. If you jump these 7 levels, then you will be at the same level. Then you start both at the same pace. Then you will definitely able to find ancestor, common ancestor.
Okay. Yeah.
Very good.
So
So this is
first
the
algorithm.
what's that?
This is the first algorithm, first
This
solution,
is
Suresh.
exactly this is the first solution. Basically, we'll discuss about the second one later. But you found the actual algorithm here, right? Basically, the thing is you already have the pointers to the nodes which you want to start. That is a given. The given algorithm already giving I and H. Then
Okay.
you just need to find the common ancestor. So and the algorithm already giving like access to the parent. You are okay to access. You have a pointer to the parent. If you have pointer to the parent, this is the way we will discuss about. Next algorithm is you don't have pointer to the parent. That's a very little bit tricky algorithm. So I don't want to give both at the same time. It will confuse the mind, right?
Okay.
So, but you are very good on this algorithm. You understood what we are doing here, right?
Okay. Yeah, yeah, yeah.
So, I will tell you, this is actually this similar algorithm we solved a couple of weeks ago in the linked lists. Did you remember that?
Linked
This is
list.
exactly the same algorithm. I thought of explaining the linked list, but you already got the actual solution here. That's really good. But
Oh,
if you are, but the people who may not catch this solution, I would start with the linked list. But you are already smart and you found the actual solution right away. So
okay.
that's good. So basically, we solved this problem before. Let me show you what I mean. So this is exactly. Did you remember? Um, Basically, the question is, tell me. Basically, the question is, hey, find the. There are two linked lists. Find the node where they meet. Let me show you the actual question here. If you go to linked list, we solved the problem.
If two linked lists intersect, right?
Exactly, exactly.
Okay,
Intersect.
okay, okay. I
Exactly.
remember, I remember, yeah.
Yeah, what is which number is that I'm trying to see? Yeah, here is the thing. So determine if two linked lists intersect. If yes, return the intersecting node. Node. The intersection is defined based on reference, not by value. So
Value.
this is the same thing here. In the tree also, it's based on the reference, not by value. So
Okay.
we already solved this problem. So how that works is like this. There are two linked lists, right? So linked
Mm.
list we will do like this. And here is one linked list, and there is one more linked list. So basically, the two linked lists here, they will finally meet at the same end. This is the ending, right? So this is the head of the linked list. This is H1, this is H2. This is the head one, this is head two, right?
Okay.
So these two linked lists meet at this point. Let's say we have something like this is head two. I
Okay.
don't want to put at the same location. So now, so this linked list has how many elements? H2 has 1, 2, 3, 4, 5, 6. But what is the linked list one? How many elements it has?
It has.
One, 2, 3, 4, 5. Did you remember what we did
Uh,
in that algorithm? The same thing, moving using
algorithm.
the same
If we
basically what we did.
compared two
Yeah,
linked lists, one is
hmm,
short, another one is long.
exactly.
Uh, uh, we
We took the same pointer approach. We took P and Q, and we start with the H1 and this one, and we'll go with the same page and we'll see where they meet. But the same problem will appear. If you start here, this is just 5 nodes, and if you start here, this has 6 nodes. So you will definitely not able to find the intersection if you are doing just like starting with that. So first again, we did the same thing. If you remember the algorithm, we will find how many elements in this one, how many elements in this linked list, and we do the difference, and we navigate the bigger tree, bigger no bigger linked list, that many elements, basically the delta. So
oh
6
yeah,
minus 6 minus 5 here equal to 1. So
one.
the bigger linked list is here. That bigger linked list, we will navigate this delta number of times. And now here we are here. This is
Okay.
P, this is Q. Then we will go at the same page. If you go at the same page, P will point here, Q will point here. These are not
Okay.
equal. And P will point here, Q will point here. Both are meeting
Yeah.
at this location.
Yeah. Yeah.
Then P equal to Q. Then we found intersecting node.
Okay. Yeah.
The exact same algorithm. If you think this is the root, and this is the children, and this is another children, so this is a tree, right? If you are
Yeah.
thinking from the end, this is, let's say, this is the one which doesn't have any next node is the root.
Mm. But in
Just
linked list, we traverse the whole uh, nodes until we find the tail, right, Suresh? to get the size of the linked list.
Yeah,
The
size
HV.
of the, in order to find the size, there is no way. You need to start from here and find 1, 2, 3, 4, 5, and you need to start from here 1, 2, 3, 4, 5, 6. You need to traverse all the way here to find the length of linked list 1 and length of linked list 2.
Mm.
Basically we do the same thing here. Basically, let's say you don't have the level, you don't have the you have only data left, right, and parent. You don't have the level. You are not maintaining level data, level variable. Then what you do, your I is here. Let's see what is the depth of I. 1, 2, 3, 4, 5. I is 5. And what is the depth of H? 1, 2, 3, 4, equal to 1. So you do the same thing. You go all the way to the top and find the depth.
Okay.
Same thing here, right? In the linked list, what we did, we navigated all the way from start to the end and the node and find the length of linked list. We don't call depth because depth only depth only applies to trees, but length will applies to linked list, right? So length of first linked list is here is 5, and the length of the second linked list is 6. 5 minus 6 equal to -1, but we don't take the minus value. We'll say, hey, difference is one level, just navigate one time the larger linked list, whatever the large linked list, navigate the delta number of times, and then start at the same time. Like now navigate both at the same time, P and Q.
Okay.
Got it, right?
Yeah, yeah, I got it.
Yeah, basically that algorithm is already here. We are readily available. We
Okay.
can I can show that, because that will give you more idea of this algorithm, because both are exactly the same, just little bit difference in terms of the implementation, but the algorithm is same. So here is the node, right? We have node, we have links. This is a node, is this is a linked list node. That's why you have only next is the only one, right? You don't have left or right or anything. Linked list. Here is the first linked list. Here is the, we added these nodes. Okay. Now let's look at the algorithm. Here is the find intersecting node. What we did. Step number 1, find the sizes of and tile element. Size and tile elements. See, the result one will give you tile element. If the tile is not null, compare the tiles nodes, last nodes. If they are not equal, the lists are not even intersecting, right? Let's say I will give you the uh, two linked lists like this. Size is 4 here, size is 3 here, but the last node is not even same. Are you following?
Yes, Sureshi.
So if the last node is not same, there is no point. We can just say, hey, these are not, there is no way they will intersect. Correct? If the last node is same, then we can see, oh, there could be an intersection here. If you start from here, you've gone all the way to this node. If you start from here, you've gone all the way here, and finally you stopped at the same node. If you did not stop at same node, that means these two are not even intersecting. Those are completely separate linked lists. Correct? You don't need to do any navigation or any other things. That's why we have this condition here.
Okay.
If the tail nodes are not same, if the tail nodes is not same, that means it's simply written there is no intersection. Now the step 3 is, if the control comes here, that means tail node is same, right? If the control
Yeah.
coming here, that means the tile node of result 1 equal to tile node of result 2. So now we will find the size. If the shorter list is like, if the size is less than result 1 less than result 2 size, then list 1 is shorter. Otherwise, list 2 is shorter. And if otherwise the longer, we need to find which is longer. List 2 is longer, otherwise list 1 is longer. So by the time we come here, we know which is the shorter, which is the longer. Okay. Now advance the pointer in the longer list by the difference of the elements. Right? That's what we did. Hey, let's take the Let's take the longer list, and we'll do the math.abs absolute size. So it will automatically convert the negative value into positive value, right? So we'll take the absolute of the size 1 minus size 2, and then we will advance, that many times. So get kth node means basically you start from here and you advance this many number of times. Okay.
Okay.
Now at this step 5, you already at the same level. Basically, in the kind of tree terminology, you are at the same level, and you're starting at the same speed. In terms of linked list, format, you are at the same distance from the intersection. So basically you are here and you are also here. That means these two are exactly the two nodes or three nodes away from the intersection point.
Mm.
Now you start at the same thing. Is P and Q are equal? No. Let's go to the P here and Q here. Is these are equal? No.
No.
Let's go to the next node. Then finally we will be able to find the intersection node.
Section node. Yeah.
Intersection node. That's exactly we are doing here. If shorter not equal to longer, go to the next node. Longer equal to longer dot next, shorter equal to shorter dot next, until you find. So at the written, like at the step 6, simply written longer or shorter doesn't matter. Basically, both are same. Whenever this while loop ends, the while loop ends only if both are same. They will definitely be same at some point. So we can use this either variable shorter or longer because both point to the same node. You understood this problem, right? This is the one we discussed a couple of
Yeah.
weeks
Leaf
ago.
situation. Yeah.
So it will follow the same pattern. So now I can show the code of this one. Okay.
Okay.
So this is the way I'm building. So I created, as I said before, data. This character is the data, and the left,
Left,
right,
right,
parent.
parent.
So we are maintaining all four. As I said, that's a good option. You said we can maintain the level, which is a really good option. I really like it because if you are maintaining level, you don't need to go all the way and compare, right? Like if I start from I and H, first you need to find the level of I and level of H,
Which, yeah. If they
because
are in the
in
same
my
level,
algorithm,
we can
yeah, in
compare
my
them.
algorithm, I did not maintain the level. But if you maintain the level as you are inserting, it will put the correct level, which is also good. But at this in the algorithm which I wrote, I did not maintain the level. So now let's find how to execute the algorithm. So here is the nodes I created A, B, C, D, all the way to the I, exact same tree here. Now what I'm doing here is, see this, A dot left equal to B, and A dot right equal to C, and at the same time B dot parent and C dot parent equal to A, because I need to set the parents, right?
Mm.
I no need to set the parent for A, because A node, if I don't set it, A dot parent is always null. That's a default value of pointer, right? So I no need to set the parent for A, but I need to set the parent for B and C. That's what I'm doing here. B dot parent and C dot parent equal to A, because parent is same for both nodes, right? You understood this point?
Yeah, yeah, yes.
Yeah. Now same thing. I'm creating like a B dot left equal to D, B dot right equal to E, and B dot parent and E dot parent equal to B.
B.
Okay.
Okay.
I'm just building the tree. This is just a building the basic tree. So I built all this tree. So now here is the algorithm. Common ancestor using parent links. So this is approach one. There is approach two, which we will discuss next week, like a common ancestor with no parent links. Without using the parent, we can also find common ancestor, but we will discuss next week. So let's discuss the first one, common ancestor using parent links, right? FCA, first common ancestor. And what are we doing here? We are just sending I and H. So I and H are here. I is here and H is here. So now it should return B, right? Let's see how it works. It is approach one. So it is little complicated. The reason is we need to write three methods, not only just one. So here I wrote three methods to execute. First one is the a method called depth. Basically, since I'm not maintaining the level, I need to find the depth of each node, right? So
Mm.
here is actual algorithm. We got P and Q. P could be any node and Q could be any node. We don't know where the P is. We don't know where the Q is, at what level. We don't know. That's why I'm finding depth of P. Hey, let's get the depth of P. Depth of Q. Let's get the depth of Q. Depth is basically means how deep it is, right? From the
Yeah.
parent, from all the way from the root, how deep it is. So we will get depth of P and depth of Q. How to calculate the depth? Let's go here. You are at some node. You need to find. You need to go all the way to the top, and you need to count the levels, right?
Yeah.
So simply depth is equal to, like, we are initializing 0, and as long as node is not equal to null, the node becomes null if you are going parent, 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 parent. Finally, if you go to the parent of A, then the node becomes null, right? So we are
Yeah.
simply saying until node not equal to null, go to the parent, node equal to node dot parent, and we are incrementing the depth. So if you start from I, depth equal to 1, G, depth equal to 2, D, depth equal to 3, B, depth equal to 4, and A, depth equal to 5. 1, 2, 3, 4, 5. And now node becomes null.
Mm.
Node becomes null and the loop will exit and a 5 will return. That is the depth of I. Correct?
Yeah.
You're starting from here. Basically, you need to start from root. But if you start from root, you don't know where the I, whether I is this side or this side. It will confuse. If you start from root, we don't know, right, whether you need to go left or right. I is here. That's why it is always better to start from I and count the depth, because you have access to the parent very easy. You have, this is very handy for you,
Okay.
because you have a parent node access. You can start from here, and let's count how many number of nodes all the way to the root. That's how we calculate the depth of P and depth of Q.
Cool.
Okay.
Okay. Suresh.
Yeah.
Yeah. We had a condition like in the tree. We compared E and H, ancestor of E and H, right?
Ancestor
Which
of
E
E
and
and
H,
H.
which is
Yes.
E. So
Which
if
is
we
E.
are, which is E.
Mm-hmm.
Yeah, we came up with a solution like that actually in our board.
Oh, in the whiteboard.
Yeah, in the
Yeah.
whiteboard.
Yeah. So if you want to know the ancestor of E and H, here is the thing. E is the
Yeah,
answer, right? But
yeah.
before that, you need to calculate the depth first. What is the depth of E?
Depth of E is uh, 3.
3, right? Because A, B, E.
Yeah, 3, and its
This
H
is
is
1,
4.
and H is 4. And what is the difference?
1.
Difference is 1. That means which is the longer, which is the second one is longer. This is P and this is Q. So Q is longer. So what you do, you will jump one time, because that's the difference, right?
Okay.
Now both P and Q will point to the same node, E and E.
Okay, okay, then it will be right.
Yeah. The same logic will work for any node. You can take K and H, or I and H, or E and H, doesn't matter. Or even I and C. Let's, if you take I and C, what is the common ancestor for I and C?
Common ancestor for INC is A.
Exactly. Yeah, we need to see whether that will come or not. Because if you take I and C, what is the depth of I? Equal to 5. What is the depth of C?
Equal to 1. 2, 2, sorry.
No, 2. Yeah. So difference is 3,
2.
and 5 minus 2, 3, right?
Yeah.
So now which is longer? This is P and this is Q. So P, the list with P is longer. It's kind of linked list. You can think of as a linked list. So P, the linked list pointed from P is longer than the linked list pointed from Q. So You will navigate P 3 times.
Okay.
Navigate in the sense go to the top, 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 parent, parent, parent in the tree. This is the kind of tree. If it is a linked list, next, next, next. That's what we did here, right?
Mm. Yeah.
Next, next, next. You will go to next, next, next until you find the until both are at the same distance from the intersecting node. Similarly, here what we do is we'll go to the parent, parent, parent until both are at the same level. So if you do 3 times, what will happen? G, D, B. Now both are at the same level, B and C at the same level. Now both will go to the parent and they will meet at the A.
Mm.
Simple. A is the answer,
Okay.
right?
Okay.
Yeah. So in this algorithm, there is one more thing I want to tell you here. In this algorithm, you never you never start from the root. You always start from the bottom. You started from I and you calculated the depth using the depth function, where you will see all the way to the parent when you until you reach null. Let's say
Okay.
I and H. You started from H and you go all the way to the parent until you find the null value. So you never started from root.
Okay.
So in this particular algorithm, you don't need to know the root. I don't care. I don't care who is the ancestor of the whole big family tree. As long as I know who is like A and B. A is one guy in the tree in the family tree, and B is another guy in the family tree somewhere. We don't know somewhere, but I can easily find the common ancestor without knowing who is the grandfather of this whole family tree, who is the root. We don't need to know the root.
Mm.
Basically, you're not starting from the root, right?
Yeah.
In a you're for, even to calculate the depth, you're starting from this node. Even to calculate the depth of each node, you're starting from that node. And in order to calculate the common ancestor also, you're stopping. As long as both pointed to the same node, you're stopping.
Okay.
So this particular algorithm doesn't require to have a reference to the root. Okay, and I will tell you one more condition here. That is the problem here. There is a problem also. Is a benefit and also there is a problem. So, oh my God, I cannot even erase properly. This is so many notes here. So the problem here is so since you don't get the reference to the root, what we get is the input is only I and H. Let's say the example I and H. You will get the reference to the actual actual nodes in the input, right?
Mm.
So now let's say I'm giving you something like this. Calculate the common ancestor for I and J. What is the common ancestor for I and J?
I N J. There is J.
Exactly. There is no J, right? How do you know there is no J? You look you by using your eyes. We looked at the tree. We will see A B C D E F G H I, but I don't see J. You simply say there is no J.
Mm.
But how the algorithm know that there is no J?
By working out on
Let's say,
all the end of the tree.
yeah. So let's say there is something like this. J. Sorry, there is something. There is something like. Come on. Come on, erase, erase, erase. I don't know why it's not erased. Okay, there is something like this. What is meant by that is there is a separate tree where the root is K and the kth right node is J.
Mm.
Now, now you got your algorithm got 2 pointers. One pointer is I, it is I, and another pointer is J. We don't know your algorithm should be able to handle all the situations. So basically, your algorithm got 2 pointers and you need to find common ancestor for this. Basically, what is the problem here is you got the reference to the two nodes from the two different trees, completely two different trees. Just like who is the common ancestor for you and me? Really
SD
difficult to find.
equals. Yeah.
What is
Okay.
that?
SD. Yeah, that's where.
SD, that's good one. That's a good example. Or God is the common ancestor. You can say somebody, everyone need to connect to the, you know,
Yeah.
connect at the God level. So this is the problem. So if you know if you are getting the pointers to completely pointers to the nodes which are completely in different trees, what is the actual in terms of algorithms in this algorithm? What is the common ancestor for I and J? What do you want to return?
It's null.
Exactly. That is our God in our programs. If you don't know, simply saying null, right?
Yeah.
So the algorithm need to return null in this situation. So if you follow the same pattern, what are we doing here? Basically, we are calculating the depth of each node. What is the depth of I?
Depth of I is 5.
I. What is the depth of J?
Depth of J is null.
No, depth of J. Look at the tree.
There is no J.
There is no J. J is here.
Oh, okay,
J.
okay. Yeah, yeah. One, one, one.
Are you sure?
Sorry, two, two, two. K and J.
Yeah. So K and J. K is the root and J is at the second level. So depth of J is 2. So now if you follow the same pattern, what you do? You do the difference. You find the difference. What is the difference? 5 minus 2 is 3. Okay. Now what you do? You go 3 times. I to Z, Z to D, and D to B. You are at the B. Now P points to B and Q points to J. Right? Now
Yeah.
what you do? You do the same algorithm. You go and compare, is B and J same? No. Now Q points to A and P points to A and Q points to K. Is A and K are same? No, right?
No.
And what happens? P points to K's parent. What is the case? A's parent? P points to null
Null.
and Q points to null,
Yeah.
because you go all the way to the parent, right? Now
Parent.
null and null are equal.
No.
What?
Yes, null
Null
and
and
null and equal.
Yeah, null and null is equal. So God and God is equal. you know, Shiva and Vishnu are equal.
Okay.
So, so null and null is equal. Then you simply written, okay, you found the common ancestor. What is the common ancestor? Null.
Null.
So if you
Okay.
find null, what you do? If you get the null value, it is the responsibility of the calling program to display correctly. It is not the responsibility of your algorithm. Your algorithm is saying, okay, we found null, take the null and enjoy. What is the null dot data? No, null dot data is
Okay.
not there. You cannot even display the data. Hey, this is the name of your common ancestor. But null, there is no value for null. So the calling problem, the program who is calling your algorithm will take care. Okay, if the value is null, I will display saying there is no common ancestor for the given nodes.
Okay.
That is not our problem. That is the problem of the program who is calling. See this one. I created, as I just said, I created J and K. Okay, and
Okay.
J dot left equal to K. Of course, left or right doesn't matter. I created K as a no as a child node for J, and parent is equal to J. Now I am calling D and K. Of course, not H I and K. I called with D and K. Oh, sorry. See here, I created a J as the parent. Here I created J as the parent and K as the child. Okay.
Okay.
Now I called D and K. Now if we get null value, I'm printing like there is no common ancestor of D and K. They are they are
Two
from two different trees. If you did not get null, that means there is some
data.
common ancestor. K dot data. You
Mhm.
following? So
Yeah.
that's how it is. So anyway, so we are actually, I forgot, like I deviated from the actual algorithm. So first step is to calculate the depths. Okay,
That's
and here I'm printing depth of Depth of P is this one, depth of Q is this one, and then you are calculating the delta. It's step number 2. That's getting the difference, right?
Okay.
Now, if you get the difference, you need to find what is the first node, what is second node. First node is basically if the delta is greater, that means Q is the first node. Basically, first is the smaller, shallower node. It is the node that touches the first from root. That means basically this node, basically the node, the node, the first represents the node which is very near to the root. Second represents the node which is deeper, which is the deeper node, which is very far from the root. It is the node where its path from root is longer than the path from root to the other node.
Mm.
Basically, you need to find which is longer, which is shorter, right? So
Mm.
it is a little bit tricky condition here. If the delta is greater than zero, that means when do you get the delta greater than zero? When the P is bigger than Q, the depth of P is bigger than depth of Q, right?
Mm.
Let's say 5 minus 4. That
Yes.
means that means that means Q. The Q is the smaller node. Q is the first node you will see from the root. Otherwise Q. Otherwise P. If the delta is less than zero, that means like let's say 3 minus 5. 3 minus 5. That means 3. So P will be touching like P is just 3 level and Q is at the 5th level. So that's why first node is the P. In that situation, it is P. If you get the minus value, P is the first node. If you get the positive value, Q is the first node. Similarly, it is a different second node. If the delta is greater than zero, P is the first node. Otherwise, Q. So anyway, these two are little tricky. Just carefully, by putting the values, you can figure out. Okay. Now you got the second node. Now you need to proceed. Go up by delta. Basically, you need to go this many times, right?
Yeah.
You found the delta, but you need to jump that many times before comparing. So
Mm.
move deeper node up. That's what we are doing. We are by using this method. What are we doing? We are moving from the deeper node to this to make sure both are at the same level. That's what we do here. So delta is greater than zero. As long as delta is greater than zero, node not equal to null, node equal to node dot parent. Go to the parent, go to the parent, go to the parent until delta equals zero. Delta means the difference, right? In the here is the delta. You calculate it as 1 here, and basically the difference between the depths.
Yeah.
So you will go up until that delta becomes zero.
Zero.
So now at the line number 103, what is that? Now move upwards from both, no, upward, maybe upward. So move upward from both first and second and find where the paths are intersecting.
Okay.
This is the actual while loop. So as long as first and second not equal, and first not equal to null, second not equal to null, first equal to first dot parent, second equal to second dot parent. It is just like our linked list.
Yeah.
Next equal, like if you look
Ne-
at our
One
algorithm,
into
right?
next.
Exact same thing here. See this one, shorter and longer. As long as they are not equal, shorter equal to shorter dot next, longer equal to
One
longer
equal
dot
to log
next.
dot next.
Same thing here. It's instead of next, you are calling parent because you are going up. Linked list, you go to the next node, but here you are going upward in the tree.
Mm. Okay.
Okay, you are almost done here. So now, finally, if if first equal to null or second equal to null, then return null
Open
because
null.
if any
None.
of these
No
basically
common
null,
parents.
there is no common. Otherwise you can return anything at this point. That means if this is not null, or if this is not null, that means both are equal. So at this point,
Okay.
both first and second points to the same intersecting node, and this is the first common ancestor of the given nodes.
Okay.
And finally we will return that, and then we'll print that value.
Okay.
Yeah, it's very complicated, but it takes a lot of time to understand. So
We
Thank you
have
for
to derive the conditions properly. That's where the trick
so many
is.
conditions.
Yeah.
Exactly. But the thing is, in the actual interview, they don't expect you to write 100% correct code. As long as you explain the algorithm, as long as you're able to write at least one of these methods perfectly, at least I showed you three methods, right?
Yeah.
The depth, go up by, or the main method here, common ancestor. If you write this method is perfect, then you will get 100% marks. You don't need to, in fact, you don't need to write these two methods, go up by or depth. You simply say, hey, I will calculate using some while loops.
Mm.
They don't ask you, as long as you're able to write this actual method properly, then they don't ask you to write this method. If you're able to knock this down, you should definitely able to write the other methods, right?
Yeah.
Because they can understand, okay, you are smarter to write the actual algorithm, and these are just helping methods. This is just this is a helper method